Hey everyone, can you all hear me? Okay, awesome. Looks like we're good. Yeah, I'm curious what everybody thought of that round. Did you guys think it was easy or hard? What did you guys think? Oh, I'm not sure if my... Okay. Oh, a lot of responses all at once. Okay, let me see. Yeah, I thought it was quite hard. And I I basically thought E, F, and G were all quite hard, and then B was this um, also this weirdly hard problem where I definitely thought C was easier than B, and it looks like the rest of the participants generally agreed with me. Um, yeah, E was tough to implement. Yeah, it looks like you guys are generally on the same page. The problem B was tricky, and then big gap between D and E. Didn't know how to solve A. Yeah, we'll go over all of the problems here today. So yeah, for me, I definitely had a bad strategy here. I think at the beginning I was fine. I did A, and then I was working on B, but I saw a couple solves on C, so I went to that. Went back to B, and then actually figured that out quickly after kind of coming back to it for a second time. I was kind of stuck the first time looking at it. Then went to D, and so A, B, C, D were all pretty good. And then after that, I looked at E for a bit, um, didn't immediately come up with a solution, and then actually started looking at F instead. And so I started going for F. Um, so I right on F to begin with. So I had some issues in my solution. I actually missed a couple things that one was caught by the samples, and then I had some bugs that I had to fix. So I got a lot of wrong submits here. So I first submitted at 48 minutes, but I finally got it at 84 minutes. So that's a pretty big gap there of just like fixing and debugging. And I also realized I actually had to run some stress tests, and I realized that there was another case that I didn't quite handle, and so that basically didn't go as planned. Problem F, it didn't go too well. Um, it would have been a lot better to just like spend more time thinking through it and like being a bit more careful about it instead of. I think I just jumped into code too early and then ended up having to backtrack and rethink it a bunch. And then it was kind of just a scramble to get one more problem E. I don't think I did it in the cleanest way at all. I just kind of threw a bunch of things together to finish it. But yeah, I'm curious if you guys in the chat have some different or better solutions for me. Yeah, looks like a lot of questions about problem B, so we can jump into the discussion there. Unc Kyle said audio not syncing. I think the audio seems to be fine for everyone else. If there are audio problems, just let me know. And if a lot of people seem to have problems, then I'll try to figure out what's going on. But yeah, Mizu Live says audio is good for me. Okay, yeah, let's just walk through the problems then. Um, so for problem A, we've got an infinite two-dimensional grid, and we can just make moves in the normal directions, north, east, southwest, or we can stay. And we want to go from 0, 0 to xy as quickly as possible. And xy are non-negative and between 0 and 10 to the fourth. And so we just want to get there as quickly as possible. The key thing is that we cannot repeat the same command twice. And so basically for this problem, there's going to be a certain amount of times we want to go east and a certain amount of times we want to go north. And we kind of want to alternate that. In the case of x equals y, so for example 5, 5, we can just alternate perfectly, like in the example northeast, northeast, and so on. And so it's just the sum of these two, which is 10. But in some cases, for example 7, 1, we're going to have to go east a lot more times than we go north. And so we can't actually get 8 because we would have a bunch of times where we'd have to go east twice in a row. It turns out that we actually never need to use south or west. The idea is if we're using a south or a west to try to like even out the commands, and so we don't have 2 in a row, it would be better to just use a no-op, right? Because for every south that we do, we have to do an extra north to cancel it, and then for every west we do, we have to do an extra east to cancel it. So the key thing is we just use norths, easts, and stay commands. And that way, we only need to do basically the max of these two plus, well, there's 2 cases. One case is if they're equal, then it's just a sum. Otherwise, it's the max of the 2 plus the max minus 1. So in this case, for 7, 1, it's 13, because we can just alternate, we can just imagine doing, what is it? We can just, imagine east, stay, and so on. So that there are 7 easts and 6 stays, and just replace as many of the stays as we need to get this. And so the code is really simple. It's just, so I just do a swap to make sure y is the bigger one. And then I do y plus the maximum of x and y minus 1. And that takes care of the equal case and the non-equal case. Okay, so we can jump to problem B. A lot of people have questions about that. So for this one, basically, the key thing is we need to make the sum of everything divisible by n minus 1, right? That's because at the end, if we want one of the boxes gone and we want everything else to be equal, then clearly it's a multiple of n minus 1. The other thing that we need, Raven is having a bad internet connection. Yeah, I'm planning to upload this to YouTube afterward. So if your internet connection is really bad, feel free to check it out later. But yeah, so for this, we need the sum to be a multiple of n minus 1. And then it turns out the only other condition we need is that the sum needs to be at least the biggest value in A times n minus 1. And the reason for that is, imagine we have like an array A that looks like, for example, 0, 0, 0, 100, right? Then we need the sum to be a multiple of 3. So in theory, the smallest sum we could get that would be a multiple of 3 is 102. But that's not going to be any good because if we, for example, if we add 2 to this element, there's no way we can like balance out this 100, right? So as long as we have a sum that is at least as big as the biggest number in here times n minus 1. So for example, in this case, we would just add 200. And it actually does not matter how we add that 200. Or sorry, that's not true. It does matter how we add the 200 because we need to make sure that the maximum element in the array stays 100 or below. So in this case, when we add 200, as long as we keep everything 100 or below, it doesn't matter how we add it. So we can make it like 100, 100, 0, 100, or we can make it 50, 50, 100, 100. And all of these arrays would be fine. The reason for that is basically if we imagine knocking out any one element, right? So we have 50 extra to add to these 3. Then because we have we have enough total sum to make everything greater than or equal to this max value, and nothing in the array is greater than this max value, then clearly we can just add up values to hit everything equal to this max value. Yeah, it's a little tricky to explain. Does that kind of make sense to everyone? So actually, all we need to do really is just to figure out how much we need to bump up the sum so that it is both a multiple of n minus 1 and it is at least as big as the biggest number in A times n minus 1. So maybe we can look at the code first and then go back to the explanation again, just so the idea of what we're doing here is clear. So we're just reading n, we're reading the array A and sorting and getting the sum. Just save that as original. Yeah, so first thing we do is make sure it's divisible by n minus 1. I think we don't need to do this part because we do it again here. But yeah, I think we can just get rid of this. Let me just make sure that still passes samples. That seems fine, yeah. So basically make sure the sum is at least a dot back times n minus 1. And then beyond that, we also need to make sure that it's divisible by n minus 1. And that's the sum we're going to take, and then we take that minus original. Okay, let me think for a sec how to explain this a bit more clearly. Okay, so there's basically two cases. The first case is we have an array. For example, let's say we have the numbers 1, 3, 7, 9. And in this first case, the sum of the array is less than the biggest value times n minus 1. Okay, and so basically the claim is that, well, first of all, if the sum of the final array is less than the biggest value times n minus 1, then we can never do, or then we're never good, because we would need every element. Basically, if we throw out some element, right? If we pick 3 as the element we're going to remove, we need to distribute the sum of 3 somewhere, right? Let's say we put it here. The sum of this array is still the same as the sum of the array before the operation. And because this sum is not big enough to make everything equal to 9, something will be less than 9. And so there's no way all the elements can be equal. And okay. And then the other case is if we get the sum of the array, if any way we add the values somehow so that the sum of the array is greater than or equal to the biggest value times n minus 1, and sum A is a multiple of n minus 1, then we can do the operation. And basically the reason for that is sum A is going to be equal to x times n minus 1, where x is at least the biggest value in A. And so we can just, no matter which element we remove, we can just get an array which is just n minus 1 copies of x. So for example, if we have the array above and we get it to, let's say, 6, 7, 8, 9, right? And the sum of this array is going to be 30, right? And so this satisfies the conditions above. It's at least 9 times 3, which is 27, and it's a multiple of 3. Then no matter what we take out, for example, if we take out the 7 And we can then distribute these 7 across these numbers to get 10, 10, 10, which is just sum a divided by n minus 1. Okay, hopefully that made more sense. And so, yeah, so the only 2 things we need to do here, one is to make sure that the sum is at least the biggest value times n minus 1. And then the second thing is to make sure it's a multiple of n minus 1. And so that's what we do in this code. Pretty simple. And then we just calculate the difference, how much more we added. Okay, it looks like that makes more sense to people. Okay, let's jump into problem C. Okay, so in this problem, you're given a string containing parentheses and brackets. And what you want to do is you want to remove, in one move, what you can do is you can remove some non-empty subsequence of your string, as long as it is a regular bracket sequence. And the regular bracket sequence is defined here. Basically, it's like you just make some sort of mathematical expression and then remove all the numbers and pluses and whatever, and you just leave the parentheses and brackets. It has to be balanced, right? So we remove one of these from the string and then concatenate the remaining parts without changing the order. And we want to know how many moves we can perform at most. So I'll just save this as b.txt. So here, if we, let's say we have a string, right? And let's imagine any sequence of removals that we do. So we could remove this and then remove this, right? And so that could be our sequence. And the main thing to notice here is that if we ever remove anything that is more than just a single pair of matching parentheses or brackets, we could have actually done better, because we could actually just split this into first removing this and then removing this, right? So the main idea is this would be better. And so the only things we actually need to consider removing are just matching pairs of parentheses and brackets. And so we can just do that super easily with a greedy algorithm. We just go through, and here the way I coded it is I just kept track of the number of left parens and the number of left brackets. And then every time I see a right paren, I try to match it with one of those. Every time I see a right bracket, I try to match it with one of the left brackets. And when we do match, just answer plus plus. And so that's how we get the answer. Unfortunately, I do not have a drawing pad set up, so I'm just drawing in ASCII. Yes, I will upload this to YouTube. Been getting a couple questions with that. Socket Knot says, can you please explain how to do this problem with max flow? I guess you could do that. I don't know that it will run fast enough, though, so I wouldn't recommend it. So it looks like we still have a couple questions about B. So one question is, what would you do in the case of 116? So in this case, n is 3, n minus 1 is 2, the sum is 8, right? And so we need the sum to be at least 6 times 2, which is the biggest value times n minus 1, which is 12. And so we just need to make sure that we find the smallest number that's at least 12, that's a multiple of 2. It turns out that 12 is fine. And so basically, once we know that we want to get the sum to 12, we can do it in any way that maintains the maximum value as 6. So we could do 1, 5, 6, we could do 2, 4, 6, we could do 3, 3, 6. Any of these are fine. And so the answer would just be 4. And then another question was, can you please explain how your solution for B is not TLE? So for B, yeah, so this code is going to be n log n because we have an n log n sort out of everything that's O of n. This stuff is just O of 1. And then this part maybe is the part that was unclear. But this loop can only happen at most n minus 2 times, because you can only increment so many times until you get a multiple of n minus 1. Technically, I could just do this part in O of 1, but since I'm already doing n log n and O of n stuff anyway, it doesn't really matter. Okay, cool. Let's jump into problem D in that case. All right, so on this problem, you've got, basically you've got n towns numbered 1 to n. The towns 0 and n plus 1 don't really matter here, except for you just cannot cover outside of the range. And so basically, each of the towns 1 through n has a 1/2 probability of building a radio tower and 1/2 probability of not. And then after you pick the towns with radio towers, every tower needs to pick a power. The power is going to be a number from 1 to n. And so the signal from a tower which is located in town I that has a power of p, it reaches every town C such that the absolute value of the difference between those two is less than p. So if you pick a power of 1, you only cover yourself. If you pick a power of 2, you cover your 2 neighbors and yourself. If you pick 3, you cover 2 to the left, 2 to the right, and yourself, and so on. And you want to choose your powers in a way that you don't cover towns 0 and n plus 1. And then for towns 1 through n, you cover them exactly once each. So in other words, basically the tower coverage is just like a perfect covering of 1 through n, and then nothing else. So the example they give is n equals 5. So n equals 5, and you have towers in 1, 2, 4, and 5, right? And so the way you can do it is you can have 2 cover 1 through 3, you can have 4 cover itself, and then 5 cover itself. And so that corresponds to town 2 has a power of 2, and towns 4 and 5 have a power of 1. And that way you're not spilling over into town 0 or n plus 1 either. And then the problem is actually just asking, what's the probability that after you build the towers, you have a way to set all of the powers to satisfy all these conditions? So, and then also you want the probability modulo this big prime number. And so the reason they have this modulo requirement instead of asking for like a floating point output is because if the output was a floating point, you can actually kind of cheese the problem by just assuming that you will never skip, 50 towns in a row, because the probability of that is so small that you can pretty much ignore that for the case of floating point probability. But you cannot ignore that for the case of modulo probability, and so that's why they're asking that. The best way to think about this is really, instead of thinking about probability, we're just thinking about, okay, there are 2 to the n kind of arrangements of these towns, where for each town it has a tower or doesn't. And then how many of those arrangements have a valid way to set all the powers? And so given that formulation, we're just trying to think about like, okay, if let's say we have something like this, and then the special towers are 1, and then maybe 4, and then 7, right? How would we arrange these powers? And in this case, for 1, it's clear it can only cover itself, otherwise it will spill into 0. And then for 4, it's clear you need to cover the 2 with the 4, right? And so it has a start here, which means it ends here. And then for 7, it just covers itself again. Similar reason as 1. And so it's pretty clear, actually, that if you just have a sequence of towers, that you can just figure out whether it works or not by just going left to right and doing kind of a... It's almost like a greedy, but it's not even really greedy, because it's just, you only have one option at each point, which is you have to cover, for example, for this 4, you have to cover everything starting from the first uncovered tower, which is 2. So this can kind of come up with, or this can kind of give us an n squared dp, where the state is going to be, what is the last tower that was, or maybe it's not n squared, but at least polynomial, where the state is the last tower that we built. So for this case, it would be, it could be 4, and then also how far did that tower reach, which in this case would be, let's say, up to 6. And so that would be, I guess that would be n squared states, and then we would do kind of an O of n additional transition. So it would be something like n cubed. Gil Hermegs asks, when is it impossible? So I'll give you an example of something that's impossible. It's actually really easy, given that we know 147 is possible. We could just do, 1457, just add something else. And so then we would try to cover the 1. We would say, okay, 4 needs to cover the 2. And so we'd go here, and then we'd be like, oh, we have to double cover 5, so we have a problem. So we have this like n cubed dp with n squared states. And maybe we can think about, okay, maybe there's like a better representation than just what's the last tower, and like how big is the range of that tower. Right, so if we know what's the last tower we covered and how big is the range, that is the full state. But actually, it turns out a nicer way to think about this is, instead of doing these kind of brackets, we can have 1, 2, 3, 4, 5, 6, 7. We actually just have these kind of dividers between them. And so Dush asks, n squared dp with n states. No, it's actually an n cubed dp with n squared states. Yeah, I thought it was n squared at first, but it turns out to be n cubed. SM Sugar and Wine asks, one tower can have multiple values in different scenarios, right? So yes, so it's not like the same tower will always have the same value. For example, if instead of 147 you had 1, 2, 3, 4, 5, 6, 7, right? Everything would have a value of 1. But then, in this example, tower 4 has a value of 3. But anyway, back to this. So this is really the best way of looking at the problem. You have these dividers in between some adjacent pairs of cities. And really the only constraint that's necessary for this to work is that the number of cities in between any two dividers is odd. And if we have a division like this, then there is one unique way to pick the towers, which is you just pick the center of each section. So we pick 4 here, and we pick 1 and 7. And so this corresponds to 147. So in math terms, we have a bijection between the set of ways to pick these dividers so that everything is odd, and the set of ways to pick the towers so that it works, right? And so we can just count this instead. And so this becomes a nice simple DP where we have n states, and we can do this DP in n squared, where basically dpk is just going to be dbk minus 1 plus dbk minus 3 plus dbk minus 5 plus so on. The reason for that is we want the length to be odd, right? So and that's why we just have all these odd numbers showing up. And then, so this is an n squared dp with n states, right? But because this, transition is so simple, we can just actually manage this by keeping track of two sums. One is the even sum and one is the odd sum. And so we can just implement it in O of n. And so, yeah, my solution here, that's what we do. So ways is the dp state. It just tells us the number of ways to finish a prefix with a divider at this point. So for 0, it's just one way to do it. And then, excuse me, sums is the even and odd sum I was mentioning, where sum 0 is the even sum and sums 1 is the odd sum. So sum 0 starts at 1. And then we just go through 1 through n. The number of ways is the sums for the opposite parity. So that's why I have a not here. And then we just make sure to update the sums with our current thing. And so now we know the number of ways to finish, and we just divide it by 2 to the power of n. So people are asking about Fibonacci. Yeah, so it looks like this is indeed the Fibonacci sequence. And basically the question is like, why is this the Fibonacci sequence? And then if we can think about like Fn, so the Fibonacci occurrence is just this, right? And then we can think about kind of expanding out the last part of this. So Fn minus 2 is equal to Fn minus 3 plus Fn minus 4, right? And then Fn minus 4 is equal to Fn minus 5 plus F. Oh, I missed a couple underscores. N minus 6. Okay, yeah. So, yeah, you can kind of see where this is going. If you keep doing this all the way, then you basically get the same recurrence that I'm putting here. And so, yeah, so another thing that means is that, in fact, actually, you can solve this problem faster than O of n because you can generate Fibonacci numbers faster than O of n. You can generate them modulo something in log n time if you just use matrix exponentiation. And so that wasn't at all necessary for this problem, but just kind of a fun fact. The Fibonacci matrix. So this is the Fibonacci matrix. That's just 1, 1, 1, 0. If you take this matrix to the power of n, you'll get basically the nth Fibonacci number. And so by doing exponentiation by squaring, you can actually get the answer to this problem in log n time. Okay, so now we're on the hard half of the problems. So for these three problems, E, F, and G, I actually didn't have time to work on G today, so hoping to work on it at a later point. But for E and F, unfortunately, I would say my solutions aren't very elegant. They were both like, mostly because they were both just kind of me thinking of one thing and then starting on that idea, realizing there were some problems, and then just kind of patching the ideas together. So these are definitely not the cleanest solutions, but maybe we can think through them now and try to figure out a kind of cleaner way to think about them. Looks like we still have some more comments about D. So it's solve D by finding pattern from sample test cases, lol. Yeah, that's actually a pretty funny way um, to go about this problem. If you just brute forced for like n up to 10, you would actually see the pattern, and then it would be pretty obvious. I think that's another reason why they set up this this modulo output, where like this doesn't, resemble the Fibonacci sequence until you multiply by 2 to the power of n. Amir RZWM says, can you please explain mod part of D? Which part is the confusing part? I mean, we're just taking sums, so we're just adding modulo the value, and then the only thing that might be a little tricky with the mod is that we're dividing by 2 to the power of n at the end. But again, this is like a relatively standard bot thing. If your question is more about like how can we do probabilities modulo these prime numbers, I think there are a couple good posts. I can't remember exactly who wrote one off the top of my head, but I might try to find it later. Okay. Let's see. Yeah, so let's jump into E. Oh, we got a couple more questions. Okay, hang on. So Gilhermegs asks, why is the probability of that happening just a number of ways? The reason is that there are 2 to the n outcomes that are all equally likely. They all have a probability of 1/2 to the power of n. And so we can just count all of them and then find the number of ways that succeed and then just divide by 2 to the n at the end. Oh, what if probability was p instead of 0.5? Oh, okay, that's an interesting question. So instead of 1/2, what if this number was something given to you that was p? And in that case, I think you can still do it just fine in O of n, because yeah, we kind of just need to, we're just kind of weighting our different states by the number of sections that they have. Yeah, it would be a bit more of a complicated recurrence than this one, but I think it would still be doable. Okay, yeah, let's jump into E. So on this problem, you have M participants who just did a contest. They competed on N problems from 1 to N. There are 2 problem authors, and they're each going to explain how to do exactly K consecutive tasks in the problem set. And we can choose these 2 segments any way we want. They can be the same segment, they can intersect, or they can just not intersect at all. And each participant is interested in listening to a set of consecutive tasks from Li to Ri. And basically we want to know, out of all the ways we can choose the 2 authors' segments of K, what would be, oh, and each of the participants goes to whichever author overlaps more with the task they care about. What would be the maximum sum of the number of editorials that every participant hears that they care about? And everyone can only go to one of the 2 authors. So yeah, if anyone in chat also saw this problem, I'd be curious to hear if you have like a nice, cleaner solution. I can describe my solution. It's definitely not the cleanest. It's a bit complicated. But basically, I was thinking about, okay, so what's kind of the most obvious solution here? The most obvious thing here is, let's iterate all of the choices of the 2 authors ranges, which is about n squared choices. And then for each of those, we can just iterate through all of the participants and calculate how many problems that we overlap on that we get. And that would be, what is that? That's n squared times n. And so obviously that's intended to be too slow. Maybe if you do some crazy optimizations, you can get it to work, but that would be about 8 billion or maybe somewhere in that neighborhood. And so we probably want to get to something, given this 2000, we probably want to get to something that's like n squared log n or so. And so we can just try to think about optimizing some portion of that algorithm. So yeah, so what I did is I did iterate one of the two intervals, and then ultimately what I tried to do is figure out the answer for all of the possible second intervals in faster than quadratic time. And the idea there is basically, I might have to do some more ASCII drawing. So let's say our first interval looks like this, and then we're like considering different choices for the second interval. It could be here, or it could be here, or so on, right? We'll just assume the first interval starts no later than the second interval. Then if we're thinking about one of the participants, well, first of all, we can bump up their start point to at least the start point of the first interval, because if they're interested in any problems before the first interval starts, we obviously won't get to those. So we can just assume everybody starts here or later, basically. And then the key condition that we need to know to figure out which of the two intervals we would want to use actually ends up being not too complicated. So let's say, for example, so this is interval 1, this is interval 2, and then this is participant. Yeah, so let's say this one goes from L1 to R1, and then let's say this one goes from L2 to R2. And then let's say the participant goes from start to end. So there are kind of two cases here, whether the intervals 1 and 2 intersect or they don't intersect. It actually turns out that the condition for whether we should use interval 2 or interval 1 ends up being the same in both cases. And the condition ends up being basically min end R2 minus R1 is greater than L2 minus max start L1. And then remember that we said that we just max everything with L1 in the first place anyway, so we can just remove this max. And so this is the condition where we would want to use interval 2 instead of interval 1. And another way we can rewrite this is we can just move everything to one side, minus L2 plus start, greater than 0. And actually, Vatsal91 mentioned something important here, which is that if we think about moving L2, and also, of course, R1 equals L1 plus K, and R2 equals L2 plus K, right? So if we think about, sliding L2 and R2 from left to right, basically every time we increment L2, this will get one bigger, and so this value, let's call let's call this f of L2, right? And then this is just going to be L2 plus k because that's what R2 is. So the idea is when L2 increases by 1, f of L2, what happens to f of L2? Well, first of all, this part decreases by 1. That's for sure. And then this part will increase by 1 for some amount of time until L2 gets big enough, and then the minimum of the two is actually end. And so what that means is like, let's think about the delta, right? Like kind of the derivative, but in more of a discrete sense. So what does f L2 plus 1 minus f L2 look like? Well, it looks like for this part, it's just minus 1. And then for this part, it's going to be plus 1 if L2 plus k is less than end, else is 0, right? So basically, for small values of L2, or small enough values of L2, it's going to be 0. And then if we think about like this function g, it looks like this for a while, and then it looks like this for a while. And so what that means is that as we're sweeping L2, there's some range of time where we want to use interval 2. And then because, let me start over. So f is just like the sum of these g values, right? Prefix sums, right? Because the g values are just the consecutive differences of f. And so the prefix sums of g are just the values of f. And so what that means is f is never increasing. F is always staying flat or going down. And when FL2 is greater than 0, we want interval 2 instead of interval 1. What that means is as we're sweeping, there will be some amount of time we want interval 2. And then once interval 2 goes to the right enough, we'll want interval 1 instead. This is for a fixed participant, right? And if we think about this, this also makes sense. If we think about, if this is interval 1, and this is interval 2, and then this is the participant, right? Or rather, let's think about it this way. Right. So for all of these choices of interval 2, interval 2 would be better for the participant, or at least as good compared to interval 1, right? But then eventually at some point, obviously, when interval 2 is like all the way over here, then interval 1 is better. And then, interval 1 stays better. And so that's basically what we're showing here. So essentially, when we're doing our sweep, we can actually figure out for every participant kind of what time or like what L2 value do they switch from interval 2 to interval 1. And if we figure that out, then we can just simulate the whole thing with a sweep, just like a sort and a sweep in n log n. And then I actually ended up using a seg tree. I don't know if that's completely necessary. It ended up just being the easiest way to implement my solution. And so in this code that is more or less what I do, I read all the people, and then I iterate. The main loop is to iterate L1, and then you solve L1, and you take the max out of all of those. When we're solving an L1, I actually do a binary search to figure out when this kind of crossing point is, where interval 1 becomes better than interval 2. And so that's what this is here. Basically, this is the amount of intersection with interval 2. This is the intersection with interval 1. Figure out whether that's better or not, and then just binary search it. And so that becomes our change time. Sort everything by change time. do a sweep and also figure out the intersections with, I guess technically I didn't need to pre-compute this, but figure out the intersection with interval 1 because that doesn't change. And then I just start with everything as interval 2, sweep L2 from left to right, and then based on this change time, I start to swap people over from interval 2 to interval 1. And so the way I do that is I have a seg tree, and the seg tree is just basically it's just a tree over the n problems where each value is the number of people who are interested in that problem out of the people who want interval 2. Only the people who want interval 2. So for example, if there are 6 problems, we'll start something like this, and let's say someone is interested in 4 to 5, and someone is interested in 1 to 2, right? Then we would increment these two, and we would increment these two, and so the tree would look like, or the values in the tree would look like that. And then to query the sum of what interval 2 does, it's just a seg tree query on the range of interval 2. So that's what we're doing here. We just sweep L2 and then find all the people whose change time happens here or earlier. This is just to swap them over to interval 1, and then we decrement them from the tree. And so first we incremented everyone in the tree, right? From P0 to P1, which is the person range. When we switch someone to interval 1, we remove them from the tree, and we just add them to their, or we add them to our sum based on their overlap with 1. And so for this L1, L2 pair, the actual answer would be current, which gives us the overlap from interval 1, plus tree.query L2, L2 plus K. And that gives us all the options. Can you please explain using an example? Okay, let's see. I'll just, maybe I'll grab one of the sample cases. Yeah, so let's do this one. This is the second sample case. So here there are 10 problems, and there are 3 people, and the intervals are going to be length 3. So in this case, the 10 is kind of silly. Let's just make it like 6 because 7 through 10 don't matter. In this case, we're going to iterate L1. So if we first consider L1 starting from 1, then basically we have 6 slots, right? And so interval 1 is going to be, these are the 6 slots. Interval 1 will do that. And then we're just going to iterate interval 2, starting here, and then here, and here, and then here, right? And if we, I can also like draw the people on here. So this is the first person, this is the second person, and this is the third person, right? So on the top is the people, and then below that, this is interval 1, and then this is interval 2. And so for each person, we would compute what's the kind of first point of interval 2 where they would actually prefer interval 1. So for 2, 4, the first point where they would prefer interval 1 is actually this interval. So in particular, for 2, 4, if interval 1 is 1, 3, and interval 2 is it's 4, 6, then they would prefer this one because they get an overlap of 2 versus an overlap of 1, right? But for anything before 4, 6, so it's actually this one, sorry. For anything before 4, 6, they would prefer interval 2. But once interval 2 goes as far right as 4, 6, then they prefer interval 1. Similar thing for all of the remaining people. We figure out the time that they switch over. And so then we can just do this sweep. So for this interval, we have everyone started at interval 2, and then as we go further, we are basically sliding people over to interval 1. There are quite a few submissions that do not use segtree. Any ideas on that? So yeah, like I was saying, I was definitely like rushing through this problem. I kind of thought of the first thing that seemed to work, so I didn't spend more time to um, clean up the solution. But there probably is. I could definitely believe that there are ways to do this without kind of a big data structure. Um, I would have to kind of go back and look through myself to see what people did. What if there are? What if there are more problem setters? So I think if there are more problem setters, the problem gets much harder. Like the kind of base solution is what is it? It's like n to the power of p, where p is the number of problem setters times m, and so we're just kind of optimizing out a factor of n here. Um, yeah, so I think more than two problem setters would make it a much or like much harder problem to solve efficiently. There might be a point where interval 2 is preferred again when n is large and k is small. Do you have a specific example, Grande Sonnery? Yeah, because I went over the explanation above of why this is basically a decreasing or non-increasing function, and so it should only switch once. Long contest says, if you sort the intervals by ai plus bi over 2, then the first author takes some prefix of the intervals and the second author takes some suffix. Let me think about that. Yeah, that makes sense. I don't know if I have an immediate proof. I think the main idea is that um, basically the midpoint for each participant, if you have two participants where participant 1 has a smaller midpoint than participant 2, you would never assign them so that participant 1 goes to the right author and participant 2 goes to the left author. And if you prove that, then you're good. Let me think. Oh, I think I see. So it's basically like, let's say you have the two intervals. Then, yeah, okay, then I think which interval you take just depends on if the midpoint is before or after this point here. That's like kind of halfway between the two intervals. And yeah, I think you can show that pretty simply with just like maybe a little bit of algebra, that if the midpoint is left of this point, then you want this one, otherwise you want this one. Okay, yeah, that's a pretty nice observation. It definitely makes the problem a lot cleaner. You would just sort all of the people by their midpoint, and then you can just literally iterate over the cutoff point where you make this the prefix and this the suffix, and then you just find the optimal interval for both, which I think you can just do with yeah, you can just do that with like, you can literally just find the array of like how many people are covered at each point, and then find the like best segment of k. Yeah, so that's a nice idea. I definitely didn't think of that in contest. That would have made it a lot simpler. Ekronwall says you don't need linear time. What do you mean by that? Oh, yeah. So the problem has constraints up to 2000. Wait, does this solution give us something better than quadratic? I guess if we had some sort of seg tree or something that could query, that could do like increment this range or decrement this range and then find the largest range uh, of length k, then we would be good. And oh, I think that's just, yeah, I think we can just do that if we are, that's basically like adding arithmetic sequences to a seg tree. Yeah, okay. Yeah, so we can actually solve this problem in like n log n, which is pretty crazy here. Or maybe I should say like n plus m log n, something like that. Oh, maybe you can't do that? Add line. Oh, that's right. I think I was thinking of add arithmetic sequence and then query sum, maybe. So you can definitely do that. But query max, yeah, okay, never mind. Yeah. Add arithmetic sequence and then query max is not a nice thing to do. It can go back and forth very much which one is the max. Why didn't they have 5,000? I was very tempted to write n cubed with 2,000 for Make a Genius. So the reason they didn't have 5,000 is because they want to accept n squared log. And so for me, actually, my submission was a pretty significant chunk of the time limit. I take about half the time limit. So if n were 5,000, I'm pretty sure I would TLE. Yeah, n cubed with 2,000 should pretty much be good enough. Like 2,000 should be pretty much good enough to fail n cubed. You might be able to get it through with some pretty crazy optimizations that like are potentially beyond what I know how to do. And so I think this pretty much serves the purpose of allowing anything subcubic but not allowing cubic. And I think this is the right kind of balance point to set. You don't want to TLE, actual n squared log n solutions. Okay. Let me know if there are any more questions about E. But for now, I'm going to jump into problem F. Ravenclaw OIR says, per blood test, someone did manage to squeeze n cubed into the time limit. Well, that's pretty impressive. Maybe we can find their solution. I'd be curious what they did. Ravenclaw, do you have a link to the comment where he said that? Okay, so I found the comment, I think, but unfortunately it doesn't link to anything. Yeah, I think this is the same one, yeah. Oh wow, okay. Someone did manage to squeeze this in. I think the key thing, yeah, the key thing is to throw in these O fast and unroll loops. And someone mentioned they didn't even use the optimization to start j from I+1. And that's pretty funny. I thought that would definitely be necessary. Um, and the AVX2, yeah, this stuff is very important too. This is like factorization here. Um, yeah, I don't know a ton about this stuff. It's like pretty unpredictable to me. Sometimes I just try to throw these in and see if they make the code a lot faster. So, yeah, I mean, I guess it was worth a try here. Yeah, it is pretty tricky often to distinguish a really fast n cubed from what is potentially a pretty slow n squared log n. Like my solution, I have a lazy seg tree, so definitely not the fastest n squared log n. Yeah, maybe this is still hackable. It's possible because this is somewhat close, but this is actually not super close to the time limit. They still have a decent amount of room. So yeah, that's pretty crazy though. Yeah, maybe one of maybe someone in chat can figure out how to hack it. Okay, we can jump into problem F. So yeah, so for this problem, you have a multi-set of powers of 2. The powers can go from 0 to n minus 1, and n is pretty small. N is only 30. And you're given this count array, which is the number of copies of 2 to the I that you have. And you can do this operation where you choose any element 2 to the L, as long as L is not 0. And you can split it up into 2 elements, 2 to the L minus 1. So if you have an 8, you can split it up into 2 4s, right? Ayush, I think, I'm not sure if I have like VODs here. I think, oh yeah, this should work. Okay, so if you just go to this link and you pick the very last video, it should be already the recording of this stream so far. And then otherwise, yeah, I'll upload to YouTube. Yeah, okay, so back to problem F. You have 2 types of queries. The first query is really simple. You just modify the count array. And then the second query is to figure out the minimum number of operations you need so that you can make at least k elements with value 2 to the power of x or smaller. I know that you don't change the multiset, you're just calculating the number of operations. So kind of first immediate thought here is that the one array, or the one query is really simple. You just modify the array. And so we can kind of think about the 2 queries in a black box where we just have an array of counts and then we want to do this specific query. And since there are a lot of queries, but n is pretty small, we can solve the query in like O of n, or like maybe even O of n squared. What would that be actually? Yeah, this is like probably fine. I ended up doing it in just O of n. But basically, yeah, because n is small, we're just trying to figure out a way to solve each query in like O of n-ish. And so it's almost like just a multi-test case problem more than an actual query problem. And so we're just gonna kind of pull out the 2 query as the problem. We just want to solve one instance of the problem. And the other thing we need to note is that we need to print -1 if there's no way to do it. Okay, so first of all, how do we determine if there's no way to do it? Well, basically, if we have 2 to the I, right, we can split it up into 2 copies of 2 to the I minus 1, and we can keep going that all the way down until we get to a bunch of 1s. How many 1s do we get? Well, we get 2 to the I 1s, right? Because this operation preserves the sum. We're just splitting the number into 2 halves. And so if we have an array like this, well, then we can actually figure out, if we ignore the fact that we want to find the minimum number of operations. We just want to figure out, oh, how many, elements can we get at maximum? Then it's really just count I times 2 to the I for every I. So for example, this one is worth 2, and then this one is worth 16. And so 18 is the most that we can get here. So if we queried anything with a k of 19 or higher, the answer would be -1. If it was anything 18 or lower, the answer would be, it would be possible. It would be non--1. Or and Don, I am uploading to YouTube later. Okay, so now we need to figure out minimum, right? And there actually turned out to be a couple of different tricky cases here where I actually thought of an idea and I started coding, and then I realized I missed one of the cases and I had to fix it. So definitely better on this problem to think through all the cases more carefully before you start coding. But basically the options we have are, first of all, we can count everything that's already 2 to the x or smaller, right? And if that number is already k or bigger, we're just done. It just takes 0. We don't need to do anything. But otherwise, we have a bunch of different options we can do. So with the numbers that are 2 to the x or smaller already, every one operation we do with them gives us one more element, right? Because it splits 1 into 2. And we also can figure out pretty easily the number of, the max number we can get to this way, because it's just the sum of count I times 2 to the I for I up to x. And so those are nice because they cost 1 op per 1 extra element, right? And then when we're looking at elements bigger than x, then it gets a little bit more funky. One big thing to note that's really important is if you split a 2 to the x plus 1, we actually gain 2 elements that are 2 to the x or smaller. So that's like a 2-for-1 deal, where 1 op gets us 2 new elements. And so if we kind of start thinking in a greedy sense, we kind of just want to do as much of that as possible. That's like clearly the biggest benefit we can get, right? Because no operation can give us more than 2. And then if we kind of generalize that, if we think about if you think about 2 to the 4, let's say we want x equals 2, right? If we have a 2 to the 3, we can split it into 2 of 2 to the 2, right? So let me throw away these 2 to the power of, because it's just like a little bit nicer this way. So 4 in one operation can make 3, 3, 3 can do 2, 2, 3 can do 2, 2, right? And so this way, in 3 operations, we made 4 values. So that is also cheaper than 1-for-1, right? And it turns out we can kind of think of it as a binary tree, actually, where, okay, maybe I will draw an ASCII binary tree here. Where yeah, I probably should get a drawing tool. Oh no, we ran out of space. Okay. Yep, we're definitely going full ASCII art today. Okay, so okay, we'll just pretend these didn't overlap. Yeah, so basically, if this level is x, right, and then this is x plus 1, then what we can see is that with 1x plus 3, we can do 1, 2, 3, 4, 5, 6, 7 operations, and we can get 8 x's, right? And so 1x plus k is basically 2 to the k minus 1 operations for 2 to the k x's. And then more generally, let's say we want to get, 3 x's from this. Well, we don't actually have to like push down the whole tree. We can just take a prefix, so these 3, and then we actually only need to push this to here, and then push this, and then push this, and push this. And so we're actually just taking 3 elements in the tree, and then just counting the number of unique ancestors that they have, which is 1, 2, 3, 4. And so it's kind of this funny thing where, we can get 8 at a cost of 7, or we can get 3 at a cost of 4, right? We can get 1 at a cost of 3. And it turns out, 7 is a cost of 7. Basically, the only thing here that is cheaper than the 1 for 1 is the full tree. So there are a couple different options here. We can, once we're x or below, we can make 1 for 1, right? When we're above, we can do this kind of binary tree pushing down. And yeah, the key kind of, well, you always get an even number. Okay, yeah, sure. Technically, like, these 7, 3, 1 don't really make sense. But it's just kind of a more general way of thinking about it where, yeah, you would always want to get 8 instead of 7, or you would always want to get 4 instead of 3. But if you wanted 3 for some reason, this is still how much it would cost. It's easier to think about the halved one. What do you mean by halved one? Oh, do you mean like this level? Okay, anyway, you just think of it as right. Yeah, so that's actually like kind of what I ended up getting into. Basically what Ecknerwall is saying here. X plus k costs k to split into 1 of x plus k minus 1, 1 of x plus k minus 2, and so on. And then I guess technically, yeah, I guess we can go to 2 of x. Yeah, so basically the way that I was thinking about this was the kind of the best deal we can get is the 2 for 1 when k is equal to 1, right? And then beyond that, it's the 4 for 3 when k is equal to 2, and so on. And it turns out because of the nice like powers of 2 here, you can just more or less greedy this, where yeah, you just get as many of k equals 1 as you need, and then k equals 2, and so on, until you have enough. And I'm just going to explain this like very roughly. Until you have enough, and then there's going to be some point where the k that you have is more than you need. And so in that case, it does this interesting thing where it splits the tree into multiple trees. And so maybe that's, it sounds like, what Ecknerwall is saying here is kind of the cleaner way to think about that, where maybe you don't have to think about this one last tree, especially. The way that I thought about it is, for example, let's say we're on k equals 3, and then we only need 3 more, and the rest we can do the kind of 1 for 1 deal at the bottom by decreasing x's below, or values x and below to even smaller values. If we wanted 3 from here, we would need 1, 2, 3, 4, right? And then we actually end up getting a bunch more subtrees where this is a subtree. So because Let me see if I can highlight like this. Oh, that doesn't work, unfortunately. But we covered already these nodes, right? And so we have some kind of nodes sort of for cheap. This is a free node, right? And this is actually 4 nodes at a cost of 3. And so, yeah, basically my solution, it's not like, definitely not the nicest solution. I coded a wrong version first and then kind of kept patching it over and over until it finally worked. So this feels a bit hackier than it needs to be, but basically I do the greedy algorithm I described where I do k equals 1 to get as many 2-for-1 deals as I can. Then I do k equals 2 to get as many 4-for-3 deals and so on. And eventually a single deal ends up being more than you need. And so you just figure out the amount that you need, and then I do this idea to add these extra subtrees afterward. And so that's what this code is. I actually have to find like the smallest power of 2 in the number and then repeatedly just add that as long as it's not more than we need. Yeah, so again, definitely not the clean solution. Maybe Eknerwala has a different idea. I think he didn't do the contest yet, but I would be curious to see what your solution or code looks like. Yeah, so it ends up being, you do the 2 to the k for 2 to the k minus 1 deals as long as you can, until, like from k equals 1 going up, and then eventually one of the deals is like more than you need. So at that point, you kind of have to split up that tree into like multiple smaller trees. And so that part gets a little bit messy. That's what this code here is doing. Actually, this whole code, because this is like, we have an extra left over. And then after that, you fill in the rest with the kind of extra stuff you have at x or below, which are 1-for-1 deals. One for one is better than splitting the tree, right? So actually what I'm doing is, let me see if I can come up with an example that explains this more clearly. I think I did have I made a lot of these f-fail files because my code had a lot of different cases that it failed before it was finally right. Was this one of them? Or was it this one? Maybe this was one of them, so... Let me think. Okay, I think this might have been one of the kind of illuminating cases. So we want to get at least 8 things that are in this range. So, clearly the first thing we have to do is we have to like take this one here and like push it down to here. So we would get this, right? And this takes 3 ops, right? And so let me just double check the answer for this case. Yeah, okay, so 3 ops, and then we do 2 ops at this 2. So we actually end up with 5. And so we have 5 ops so far to get here, and we have 7. We need 1 more. The 1 more actually just comes from picking any one of these and then splitting it. And so that's 6 ops. So we need to do a combination of like bringing things down from above x down to x, and then using things that are x or below to make the extras that we need at a cost of 1-for-1. And then I think this example showed the like the last tree case. So, okay, so for this one we want at least 5 down here. So let's take this one and push it down. And so this was 3 ops, right? And then we take one more here. So we get to 0, 3, sorry, 4, 0, which is 4 ops. And then we do finally one split here. Hang on a second. Right, so this, I think there was an extra, yeah, this extra 1 was the case where you like kind of break into the tree and like grab some more trees. Yeah, so this is kind of the special case in this problem. Yeah, definitely my solution is on the messier side. It's not the cleanest. Probably after some more time to think through the problem, we could end up with something cleaner. But this is just my general approach. If anyone else in the chat had different solutions for E or F, I would definitely be curious to hear. I actually still need to solve G, so I will probably take a look at that later. But yeah, did anyone have any more questions about any of the problems? Yeah, I guess while we're waiting for in case there are any questions. Yeah, I would say overall this contest was definitely on the hard side. I mean, you can tell that just from the fact that nobody even finished all of the problems. The main difficulty, at least for the top contestants, was E, F, and G. Definitely F and G with a pretty low number of solves. F being quite tricky with like a lot of these different cases. A lot of people required multiple submits to get to F, me especially. And yeah, and then definitely some weird ordering here with problem B. I think likely the problem setters were kind of thinking that just the actual condition that we're looking for. Oh, let me make sure the slightly modified version I had still works. Yeah, so the actual solution ends up being quite simple here, but that doesn't mean it's easy. I think this is actually quite difficult to come up with. I think one thing that was really helpful for this problem in particular was just working through some examples, seeing that like when the last number or like when the biggest number in A is really big, that's pretty much the bottleneck for the problem. You have to accommodate that number, and then thinking through more, you can kind of generalize and realize, oh, as long as the sum is big enough and it's multiple of n-1, then we're good. Yeah, I watch coding. As Crow mentioned, that's a subscription problem. I can't even see it. But yeah, not bad problems though. Definitely educational. Definitely on the hard side. So I will definitely come back and look at these. Probably look at people's solutions to E and F and just look for. Well, I guess now we know the nice solution for E, but we'll probably try to think of a nicer solution to F later and solve G at some point. Yeah, so I think in that case, if there aren't any questions, that's more or less it for me for the stream. Let me see if there's anyone who we should raid. Okay, I see Ericto is streaming coding game, so I will probably raid him in that case. Yeah, I watch coding. Looks like Crow linked an explanation of the solution to the problem you were asking about. So thanks, Crow. And yeah, thanks for coming. Is it Isize? Ikize? Not sure how to pronounce it. But thanks for coming. And yeah, let me set up the raid so you guys will go to Ericto. And cool. Yeah. So that's it for me today. I'll see you guys next time.